Interactive motion mapping for real-time character control. It is now possible to capture in real time the 3D motion of the human body to drive skeleton-based animations of virtual characters. However, many characters which we may wish to puppet do not have humanoid skeletons. In fact, many characters are not vertebrates at all, and many have exoskeletons with very different morphology, or may have soft bodies with skin for which even a proxy skeleton is difficult to define. How might these motions be mapped to a human? In general, how might we map between two arbitrary motions while still giving intuitive control? Some works build animation controllers for deformable characters. However, this is limited to human-like target shapes as the source motion style maps exactly to the target. It is also possible to map multiple human skeletons to quadrupedal target skeletons, such as for this pantomime horse. However, the motion mapping is exact and cannot scale to non-human subskeletons. Our approach allows fast, flexible, and intuitive character control between widely different source and target shape and motions. We begin by interactively defining 4 to 8 correspondences, which is fewer than existing methods. Next, we learn a mapping between the source and a target latent volume using both labeled and unlabeled data. The unlabeled data serves to bound the range of admissible poses and reduces unwanted deformations. Learning is almost instantaneous, which allows the puppeteer freedom to change or alter control schemes very rapidly. Then, in real time, we generate new target sequence motions from similar input source poses. As a minimum, we only require a 3D point cloud sequence as input. The versatility of our method allows us to take input from many different sources, including body, hand, and face feature points from real-time trackers, points from pre-recorded motion capture, and from meshes modeled by hand or from multi-view reconstruction. Our mappings are somewhat robust to changes in puppeteer too. We test our method on 4 artist-created character animations: a galloping horse, a crawling caterpillar, and a sheep with body and face motions. Even with only 8 correspondences, we can create expressive animations in real time. Here, a human puppets a caterpillar with 3 sets of controls: walk, lean, and jump with arms raised. With 4 correspondences, we map a saddle bounce motion captured with Kinect to a mesh horse gallop. The speed of the synthesized motion is linked to the source. A faster bounce means a faster gallop. Next, we show mesh-to-mesh mapping from an elephant to a horse. This sequence also used only 4 correspondences. The elephant tail error is part of the input sequence. The robustness of our mapping is demonstrated here. A single walk motion is mapped with 4 correspondences, and new walk sequences in different styles are used to drive the mapping. The bold and timid human walk styles are transferred to the caterpillar. Even though the input feature set of leap motion is very sparse, we can still map fingers in fine control situations, here used for simple facial animation. In this example, we wish to control a limited range of sheep facial animation with real facial motion. With tracked facial features, our system automatically suggests good correspondence candidates to the left, which the user refines. The mapping is visualized to the right. While simple, the target sheep input was just a mesh sequence. No rigging or blend shapes were needed. Yamane et al. Describe an offline approach to map exact motions of a human character to a target creature with somewhat similar morphology. While we solve different problems, our approach produces acceptable results for a real-time solution. To show that all our method components are important, we compare against a variety of alternative approaches. Nearest neighbor approaches, and not exploiting unlabeled data, do not produce smooth motion. Direct and regularized maps, as well as point-shape spaces, produce shape distortions in the output. The jockey sequence shows the importance of using velocity features to maintain smooth motion through pose ambiguities. Due to the latent volume, even for extreme input, our method produces satisfactory constrained output. Without bounding, we can see that strong distortions appear. Finally, we puppet the sheep with body motions. Bending of the torso forward reflects in the sheep's motion, making it easier to create an expressive jumping animation. In conclusion, our method supports interactive motion mapping with few correspondences for real-time character control of arbitrary shapes and motions, and, in doing so, provides new ways to control characters for real-time animation.